Hello everyone, I am Abbas Qureshi, a research fellow at Microsoft Research India. Today I'll be going to present our work, Gender-Aware Estimation of Depression Severity Level in a Multimodal Setting. This work was done in conjunction with Professor Gail Diaz, a full professor in natural language processing at the University of Caen Normandy, France, Dr. Sriparna Saha, an associate professor at the Indian Institute of Technology, Patna, and Dr. Mohammad Hassanuzzaman, a researcher at Adapt Centre, Dublin, Ireland. Depression is a common and severe psychological disorder that has a negative effect on how one perceives things. It is marked by constant sorrow, lack of motivation, and an inability to pursue everyday activities. More than 300 million people are suffering from depression today. This is a rise of over 18% from 2005 to 2015. Typically, depression lasts from 4 to 8 months. Insomnia, emaciation, exhaustion, feelings of worthlessness, drug abuse, and a diminished capacity to remember, focus, and undertake decisions are some of the signs and side effects of depression. Its diagnosis is complex since many of its manifestations are covert. As depressed individuals don't socialize often, it becomes even harder to identify. Various methods for diagnosing depression have been researched on in the literature. A few of them are the Hamilton Depression Rating Scale, the Personal Health Questionnaire Depression Scale, Beck's Depression Inventory, and the Hospital Anxiety and Depression Scale. The increasingly rising global prevalence of depression serves as an impetus for the development of automatic solutions that can diagnose it. Affective computing is one branch of study that relies on quantifying human emotions via facial expressions, vocal sounds, and body gestures. Although a lot has been going on in this field, only a few initiatives have attempted to tackle the impact of gender information on the automatic diagnosis of depression. In our work, we hypothesize that gender information improves depression estimation. To verify this, we design and study one gender unaware model, genless, and four gender aware models, genconcat, genpred, gensp, and genasp. The five networks described before are trained using the DIAG-WOS dataset. This dataset is a part of a broader corpus, namely the Distress Analysis Interview Corpus. It is a collection of psychiatric interviews meant to benefit the assessment of disorders like anxiety, depression, and PTSD. It is comprised of 189 interview sessions. Out of these sessions, 102 are of male participants and 87 of female participants. Each of these sessions has its corresponding PHQ-8 depression score label. Each data point of this dataset is comprised of the session's audio clip, Cartesian coordinates of 68 facial landmarks, HOG features of the face, eye gaze and head pose features, continuous facial action units of the face, formant and co-rep features of the voice, and the transcript of the session. All of these modalities are sampled at a fixed frequency throughout the session, hence making them time series data. We use all these modalities except the HOG features of the face and the session's raw audio clip. This makes it 7 modalities. We group these 5 networks into 2 groups. The first group is of genless, genpred, and genconcat, and the second group has gensp and genasp. Networks belonging to a group have similar architectures. Genless, genpred, and genconcat networks are made of 3 subnetworks: the modality encoding subnetwork, modality fusion subnetwork, and the PHQ-8 score estimator. We use LSTMs to process all the modalities since all of them are time series data. The output from the last time step is fed to a fully connected layer. The output of this fully connected layer is the encoding of that modality. Since we have 7 modalities, we use 7 different modality encoding subnetworks. All these subnetworks have different number of units in their layers, so the 7 modality encodings are not of the same length. The modality encoding subnetworks are trained separately to predict the PHQ-8 score. The The modality encoding obtained from the subnetwork is fed to a linear regression unit to predict the PHQ-8 score. Once we have the trained modality encoding subnetworks, we extract the modality encodings from the fully connected layer and feed them to the modality fusion subnetwork. In the case of Gen concat network, the output of the LSTM is concatenated with the gender binary before passing it to the fully connected layer. And in the case of GenPred, which is a multitask learning network, the modality encoding is used to predict the PHQ-8 score and the gender label simultaneously. We treat the gender prediction problem as a binary classification problem. The modality fusion subnetwork is the same for GenLess, GenPred, and GenConcat. We now have all the modality encodings, but they are of different lengths. We make them of uniform length by passing them through 7 different fully connected layers. We call the outputs of these fully connected layers as the modified modality encodings. We then concatenate the 7 modified modality encodings and pass them through another fully connected layer. This layer outputs 7 values, which we call the alpha values. The activation function of this layer is the softmax function, which means that the sum of the alpha values is 1. These alpha values denote the relative importance of each modality in estimating the PHQ-8 score. We take the weighted summation of the 7 modified modality encodings, where the weights are the alpha values. We call this weighted summation as the fusion vector f. We pass f to the PHQ-8 score estimator. In the PHQ-8 score estimator, we feed f to a fully connected layer. The output of this fully connected layer is fed to a linear regression unit, which predicts the PHQ-8 score. This subnetwork 2 is the same for GenLess, GenPred, and GenConcat. The GenSP and GenASP networks are multitask learning networks. The two tasks that they handle are depression detection in males and depression detection in females. We use the multitask learning approach at the modality encoding level only. So the only difference between this group and GenLess is the modality encoding subnetwork. The modality fusion subnetwork and the PHQ-8 score estimator are the same as described before. In GenSP, we segregate the inputs based on the gender. We have 3 LSTM networks here, one for detecting depression in males, one for females, and the third one is for both the tasks. We pass the time series input of male participants to the male specific and the shared LSTM. For female participants, we pass the input to the female specific and the shared LSTM. The outputs of these two LSTMs are combined using the same fusion mechanism as described in the modality fusion subnetwork. The fusion vector obtained from the modality fusion subnetwork is passed on to a fully connected layer, which predicts the PHQ-8 score. The GenSP network has a few unwanted problems. We intend the task-specific features to be learned by the task-specific LSTMs, and the shared features to be learned by the shared LSTM, but this doesn't happen. The feature space of the shared LSTM could learn some needless features specific to the task, and the feature space of the task-specific LSTMs may learn some features common to both the tasks. To mitigate this problem, we use the GenASP architecture. The GenASP architecture builds over the GenSP architecture. The output of the shared LSTM is fed to a fully connected layer, which predicts whether the input was of a male or a female. Ideally, if the shared LSTM is truly learning shared features, the fully connected layer should not be able to decide if the input was of a male or a female. Hence, the shared LSTM and the fully connected layer act as an adversarial network, where the shared LSTM is the generator and the fully connected layer is the discriminator. To prevent shared features from creeping into the task-specific LSTM space, we add an additional constraint, known as the orthogonality constraint. Here, we take the dot product of the shared LSTM output and the task-specific LSTM output. Minimizing this dot product would ensure that the shared LSTM output and the task-specific LSTM output are orthogonal to each other, hence preventing the shared features from entering the task-specific LSTM feature space. We train these 5 networks to predict the PHQ-8 score and evaluate them. Here are the results. From these results, we make a few conclusions. Notice that gender-aware models tend to estimate depression better than the gender-unaware models. It is consistent with our hypothesis that gender information helps in the task of estimating the PHQ-8 score. A simple concatenation of gender binary value does not help in improving the estimation of depression at individual modality level. The improvement obtained by gen concat over gen less isn't very big. We also observe that multitask learning approach on depression estimation and gender detection helps in improving the performance on the first task. You can see that from the results of GenPred. Have a look at the GenSP and GenASP columns. GenASP has the lowest mean squared error for 4 out of 7 modalities. It is a strong indication that detecting depression in men is different than doing the same for women when using formant, eye gaze, facial landmarks, or head pose features. No strong conclusion can be made for the other 3 modalities, where GenPred shows the least mean squared error. We also observe that the text modality is the best marker of depression, as the mean squared and mean absolute errors are consistently lower than all other modalities. It is consistent with other studies on depression estimation. In conclusion, we hypothesize that using gender information may help in better estimating depression. To verify this, we design one gender unaware model and 4 gender aware models and train them on the task of depression estimation. We find that gender information indeed improves the performance of depression estimation, although a simple concatenation of gender binary might not be enough at the modality encoding level. We also find that for 3 of the modalities, simultaneously learning to predict gender makes depression estimation more accurate. Lastly, we observe that depression estimation using formants, facial landmarks, eye gaze, and head pose features is different for males and females.